Right, so with 2.60, we are now on sort of what you could call the final stretch in regards to the problems of Chapter 2. We have 4 more problems after this, and then we move on to 3. That being said, these final few problems are all significantly harder than what we've dealt with previously. So let's begin right away with 2.60, which introduces us to the 1 over x squared potential. We are going to solve this using the traditional Schrodinger equation, all the methods we've learned so far. In part A, we want to prove that on dimensional grounds, there is no possible formula for E naught. Now, immediately, this problem is asking us to solve a dimensional analysis problem. So the first thing I should do, instinctively, is to basically find all the units of these constants in this equation. So what do we have? We have m, which is just mass. So the units for mass are going to be just kilograms. We have h bar, which is the reduced Planck constant, which has units of joules times seconds, which is going to be kilograms times meters squared per second, because joules is kilograms times meters squared per second squared. And then finally we have alpha, which is a constant, and they don't tell us what the actual units of alpha are, but we can deduce what it is by realizing that V has to have units of energy, therefore joules. So alpha over x squared has to have units of joules. X squared has units of meters squared. So therefore alpha has to have units of joules times meters squared. Because this is the only way to cancel out with the meter squared in the denominator with x squared to make joules. So this is going to give us kilograms times meters to the 4th divided by seconds squared. So what do we mean by prove on dimensional grounds? Well, the thing we have to recognize is that in any sort of equation, constants don't interact mathematically at all. They just kind of stay on their own, isolated on one side, and eventually they get carried over to whatever other function we do. So what that means is that since in this equation on the left we have h bar, m, and alpha, they are going to sort of migrate over to the right, because this entire expression here is equal to E times psi. Psi is some dimensionless value, so at the end of the day, E has to be proportional to whatever numerical constant psi turns out to be, along with units of m, h bar, and alpha. So m to some power of a, h bar to some power of b, and alpha to some power of c. So if we write this out in terms of SI units, what this tells us is that we have kilograms to the power of a times kilograms times meters squared over second to the power of b times kilograms times meters to the 4th over second squared to the power of c. If we write this out fully, this is going to give us kilograms to the power of a plus b plus c, and then we have meters to the power of 2b plus 4c, and then we have seconds to the power of negative b minus 2c. So this ultimately has to have units of joules, because there is nothing else here that has any units. Psi is dimensionless, so these constants that carry over are the only things we have that actually have units. So because of that, ultimately this has to equal kilograms times meters squared per second squared, because this has to equal joules. So this gives us basically a system of conditions where a plus b plus c has to equal 1, 2b plus 4c has to equal 2 for m squared, and negative b minus 2c has to equal negative 2 for 1 over s squared. And immediately the problem here should become apparent, because this bottom term, if we multiply everything by negative 2, gives us 2b plus 4c is equal to 4. And this directly contradicts the second statement, 2b plus 4c is equal to 2. Therefore, based on this setup, given this potential, there's actually no possible formula for energy. We cannot obtain any valid values for energy whatsoever. Okay, so the first part of part B wants us to rewrite the Schrodinger equation in terms of these new variables, beta and kappa. So let's start off by writing out the original Schrodinger equation for this problem, which is going to be negative h bar squared over 2m multiplied by the second derivative of psi with respect to x squared minus alpha divided by x squared multiplied by psi, and this is equal to e times psi. So immediately, the first thing we notice is that we have a negative alpha term here instead of a positive beta term, and we note that beta is equal to 2m alpha over h bar squared. So what that tells me is that maybe I should just multiply both sides by negative 2m over h bar squared. And convincingly, or conveniently enough, that is exactly the reciprocal of this. So in that case, we get d2 psi by dx squared plus 2m alpha over h bar squared times 1 over x squared times psi, and this is equal to negative 2m over h bar squared multiplied by e multiplied by psi. So immediately now, this term right here is just beta. So now I have d2 psi by dx squared plus beta over x squared, as we expect, times psi, and this is equal to negative 2me over h bar squared multiplied by psi. Now over here, we have this term is just k squared, because k is equal to the square root of negative 2me over h bar. So k squared is just going to be this term right here. So therefore we have d2 psi by dx squared plus beta times x squared times psi, and this is equal to k squared times psi. Okay, the next thing we want to do is we want to verify that if the wave function psi of x satisfies this equation with energy E, then so too does the wave function psi, this time with lambda x instead of x, with the new energy E prime is equal to lambda squared times E for any positive number lambda. So immediately the first thing I'm going to do is I'm going to rewrite k in terms of E because we're changing E. So this is going back to d2 psi by dx squared plus beta over x squared times psi is equal to negative 2me over h bar squared multiplied by psi. Now, to check if psi of lambda x is a valid solution, what we're going to do is we're going to switch over to lambda x instead of just x, and this is going to cause the first term to change to d2 psi of lambda x over dx squared, and this is going to be added onto beta, which I'm actually just going to change back over as well. So this is going to be 2m alpha over h bar squared times x squared times psi of lambda x, and this is going to equal negative 2m, and this time with a new energy E prime divided by h bar squared psi of lambda x. So now the goal is to try to change this back into a single variable form for psi, and to do that we can do a change of variables. So I'm going to say r, my new variable, is going to equal lambda x, in which case I'm going to get d2 psi of r by dx squared plus 2m alpha over h bar squared, and now we have x, so x is going to equal r over lambda, so this is going to give us r over lambda squared times psi of r, and this is going to equal negative 2m e prime over h bar squared times psi of r. Now to get the derivatives in terms of r, which is going to use chain rule, so we have d psi of dx is going to equal d psi by dr times dr by dx, and since r is equal to lambda x, dr by dx is just going to equal lambda, so this is going to give us lambda times d psi by dr. Now the derivative d2 psi by dr squared is going to equal, or sorry, d2 psi by dx squared is going to equal d by dx of d psi by dx, which is going to, after applying chain rule again, d by dr by dx times d by dr of lambda d psi by dr. So this is going to equal, dr by dx is going to give us another lambda unit, so this is going to be lambda squared d2 psi by dr squared. Now we just substitute this back in. So if we do that, then we're going to get lambda squared d2 psi by dr squared, and we're going to add 2m alpha, and we're going to move the lambda at the bottom to the top, so lambda squared over h bar squared times r squared multiplied by psi of r, and this is going to equal negative 2m e prime divided by h bar squared times psi of r. Finally, we can cancel out some lambda terms here, and we get d2 psi by dr squared plus 2m alpha. The lambda squared cancels out. We get h bar squared over r, 2m alpha over h bar squared r squared times psi of r. And this is equal to negative 2m e prime over h bar squared lambda squared times psi of r. Now, the left side of this equation is the exact same as the original, only we have r instead of x. And the right side is somewhat different, but we can change it to be the exact same via substitution, because remember, we have that e prime over lambda squared is equal to e. Is that correct? E prime? Yeah. E prime equals lambda squared e. So, like that. So if e prime is equal to lambda squared e, then e prime over lambda squared is just e. So this is actually equal to d2 psi over dr squared plus 2m alpha over h bar squared times r squared times psi of r is equal to negative 2me over h bar squared times psi of r. And if we compare this to the equation we have above, let's just bring that one down. Let's rewrite it over here as this, and I'll copy it down. And if we compare these side by side, the first term is the exact same. The middle term is the exact same, 2m alpha over h bar squared, r squared, and x squared, respectively. And the back term, negative 2me over h bar squared, that's also the exact same. So therefore, we have proven that for any given valid wave function psi of x, there is an infinite number of additional valid wave functions, psi of lambda x, with lambda being any variable, with additional energies e prime equals lambda squared e. So what we've done in part A and part B is effectively we've introduced two very big problems with this potential. In part A, what we found was that there isn't actually any possible way to construct a valid energy with the possible dimensional units of joules from the constants that we have so far. So that's a problem, because what that implies is that there isn't any valid energies for this state. In part B, we said, okay, let's ignore that and let's suppose that there was a valid wave function with some valid energy for this state. Even though on dimensional grounds there shouldn't be from part A, let's just ignore part A and just keep going. What we found is that for any energy E, there's an infinite number of additional energies with additional with additional wave functions, and that's also a very big problem, because remember, we're looking at bound states. So for bound states, E is negative. So if there's some valid energy that's negative, there is apparently an infinite number of valid energies that can go more negative, because if I have some energy E equals, like, say, negative 1 joule, well, I can just keep on adding on additional positive number lambdas as multiples for that negative. So if E equals negative 1 is a valid energy, then E equals negative 4, because with lambda equals 2 would be also a valid energy. For lambda equals 3 would be negative 9, and so on and so on and so on. And that isn't physically possible, because if you really had a state that behaved like that, that implies that there's no lowest bound state energy. And since everything in the universe is always trying to get down to the lowest state, what's going to happen is that your energy state is just going to continue cascading down into lower and lower and lower energy levels. It's going to keep on releasing energy, therefore resulting in the conclusion that Griffiths comes to in the bottom, which is a state with no ground state, aka no lowest allowed energy, would be wildly unstable, cascading down to lower and lower levels, giving off an unlimited amount of energy as it falls, typically in a very explosive manner. So A and B are basically both just showing us in different ways that this sort of potential isn't actually realistically something that can occur in real life. Okay, so in A and B, we sort of showed that there were a number of problems that come about when trying to solve this potential. C is going to say, actually, we can actually mathematically solve this resulting potential. It is possible, and the resulting answer is something called a modified Bessel function, K sub ig, where ig is the order of the Bessel function, and g is equal to the square root of beta minus 1/4. We are asked to plot this function, and we are also asked to find the normalization constant A. So the Bessel function is similar to sort of the Gaussian and the Airy function and stuff like that, in that it's it's a special function that you sort of encounter a lot in higher level mathematics. The actual analysis of a Bessel function is a little bit beyond the actual scope of the course. So instead, we're just going to sort of roll with it and work with it as is without sort of trying to analyze it any deeper than we have to. So once again, we will go on Python, and actually we're going to be seeing the limitations of using Python as opposed to Mathematica with this problem, and also with the next few problems. So we will make that more, I will make that more clear as we get into it. So for now, I will stop recording and I will cut to Python. Okay, so now that we're in Python, the first thing I'm going to do is, since I'm solving with SymPy, I'm going to import everything from SymPy. So from SymPy, import all. The next thing we're going to do is we want to graph this. So Bessel functions come in a variety of types. There's two standard Bessel function types that are labeled typically J and Y. And then there's two modified Bessel function types. One of them is K. So specifically, if we want to plot a Bessel function that is the modified Bessel function labeled K, the command for that is just straight up Bessel, B-E-S-S-E-L-K. That is command for the K sub ig expression that we saw earlier in the start of this problem. So if we wanted to plot a times the square root, or in this case without a, just the square root of x times k sub ig times kappa x, and remember we have kappa equal to 1 and g equal to 4, then we're trying to plot a Bessel function of order 4i, where I is an imaginary number, with the square root of x at the front. So to do that, we're going to plot, and I'm going to set square root of, and in SymPy, if you want to do a variable, you can't just put in the variable, because then the program, Python's going to try to call whatever you put as a variable, as like a function or something similar, instead of an actual mathematical variable. So to denote it as a mathematical variable, we have to write symbols and then x. So this is going to be the square root of the mathematical symbol x, as opposed to the square root of x as sort of a Python variable. And then we're going to multiply this by Bessel, k, and the inputs for this is going to be, the first thing we're going to input is the order of the Bessel function. So in that case, that's 4i. So in SymPy, a capital I just denotes an imaginary number, and we're going to multiply this by 4. And then it's a Bessel function in terms of x. So in that case, we're going to once again write symbols x. So this basically just is written as the square root of x multiplied by the Bessel function of order ig of x, because remember there's a kappa in the front technically, but this thing is equal to 1 as the problem told us, so we're just going to set it equal to 1, and if we plot it, we get something like this. And if you zoom in more, what you'll see is that sort of the nodes, or this sort of oscillatory pattern will continue infinitely down as you, so no matter how far you zoom in, there's always going to be additional oscillations as we zoom in farther and farther. So because of that, that sort of suggests that the number of nodes on this graph is infinite regardless of what energy we actually use. So therefore suggesting that the number of energy states is infinite, which agrees with what we got in part B. Okay, so finally, this function is apparently normalizable, and if we look at this, yes, it is very obviously normalizable, because it goes to 0 at x equals to 0 and also goes to 0 at x equals to infinity. So this implies that there is a finite area underneath this graph that we can integrate to get. But this is where we're going to sort of run into an issue of using Python as opposed to Mathematica, in that at the end of the day, Mathematica really is a more sophisticated program, and it works better at dealing with more complicated functions, such as the Bessel function. Python, as we will soon see as I try to integrate this function, is not going to like doing this. So let's integrate this. So in order to normalize a, we want to take the integral of the magnitude of this thing squared. So if we square this, we're going to do integrate, which is a SymPy command, and our function. So our function is going to be, first off, the square root of x just becomes x, so I'm going to label that symbols x. and then this is going to get multiplied by the Bessel function squared. But also, more specifically, we cannot use these terms anymore. We can't use 4I as our order. Our order is instead going to be I times G. So Bessel K, and this is going to be of order IG. So I times symbol G. So this is the order of our Bessel function, and it's going to be in terms of x times kappa. So symbols x, comma, or not multiplied by symbols k, which I'm going to denote as kappa. And this entire thing is squared. And finally, we have to denote that this integral is in terms of x. So symbols x, and then also the order, or also the bounds of our integral. So this goes from 0 to infinity, which in SymPy is denoted as double O, like that. So once again, the way this is working is we're integrating the term we have above squared. So square root of x becomes just x, and then the Bessel function gets squared. And we have to do the more general form without defining specific values for g and k. And if we integrate this, what you'll see is you're going to get this. So this is called a major G function, and it is way beyond, like, actually understanding how a major G function works is way beyond the scope of this textbook. And also, if we get something like this in SymPy, what that sort of implies is that this integral is actually a little bit too complicated for it to handle. On a very basic level, a major G function is basically it's another type of special function from which most of the special functions we see in math can be derived from. So the major G, there's a formula for plotting out like what there's a way to like map this onto an actual formula for major G functions, and specific combinations of inner terms in this little mini matrix here sort of can result in the major G function equaling things like the Gaussian function, or the Airy function, or the Bessel function, or various other special equations. So this is a very complicated thing, and if we're getting it, then what it means basically is that this function is a little bit too complicated for SymPy to integrate. So because of that, I'm just going to give the resulting answer for this on Paint, and we will sort of have to move on. But this is one of the problems with using Python, in that it just isn't as sophisticated as Mathematica or Wolfram. So because of that, when you have to deal with these special functions like Bessel's, you can very often run into a number of issues. Okay, so back here, I'm going to write out the full normalization solution, which is that we want to set 1 as equal to the integral from 0 to infinity of the magnitude of psi squared dx. So in that case, this is going to give us the integral from 0 to infinity of a squared multiplied by x times the square of the modified Bessel function of order ig of kx squared dx. And what this is going to give you is a squared pi times g over 2k squared sinh of pi g. So if you move this around, then what this is going to give you is that a is going to equal plus minus k times the square root of 2 sinh pi g over pi g, like that. And that is part C. Okay, so from part A through C, we've seen all these problems with these with this inverted x squared potential, and part D explains that the reason why this is happening comes primarily from the fact that this potential has an asymptote at x equals to 0, and because of that blows up too violently. Because if we look at what this actual graph looks like, where this is x and this is v, a potential negative alpha over x squared goes something like this. And what that implies is that, well, if our boundary is at x equals to 0, this function doesn't actually ever approach x equals 0. It just gets steeper and steeper and steeper and steeper, and the limit is that it is approaching negative infinity as x goes to 0. So this actually has a slope of infinity as we go to x equals 0. So because of that, this causes kind of a problem with the potential, because this becomes sort of an infinitely deep well, and that raises a few mathematical problems and stuff like that. The solution that Griffiths offers is that we limit our potential to some point epsilon and cut it off from here. So if we cut it off at this point epsilon, then this potential is all of a sudden perfectly normal, and because of that, our resulting wave function is also not going to have the problems that it had in parts A through C. So we're asked to do two things. First off, we're asked to plot the ground state wave function for this, and second, we're asked to notice that now that we've introduced this new parameter of epsilon in this equation, in the form of our boundary states, with new dimensions of length, the dimensional analysis we did in part A is now no longer valid, and we're asked to do it again and show that the ground state energy takes on the form of E naught equals negative alpha over epsilon squared times some function of beta, where beta is the term we defined earlier on. So let's do this bottom part first before we move over to Python at the top. So we have a new variable in terms of epsilon. So by the same logic as before, constants cannot disappear when we do calculations with them. They sort of just get shifted around, and that includes constants that appear in boundary conditions, because remember, if we actually want to solve the differential equation that is Schrodinger's equation, we're going to have to plot these boundary conditions, or we're going to have to plug them in, and in order to do that, that implies that epsilon is going to appear in the actual equation at some point. So let's write out all of our variables again. We have mass, which has obviously just kilograms. We have the reduced Planck constant, which is equal to joule seconds, which is therefore equal to kilograms times meters squared divided by seconds. And then we have alpha, which we defined earlier on to equal joules times meters per second, meters squared. So this is going to give us kilograms times meters to the fourth divided by seconds squared. And then we have our new unit of epsilon, which has units of meters. So now, using the same logic as in part A, all these terms have to eventually make their way over to the right on the Schrodinger equation. So because of that, the energy is going to consist of some combination of these four variables, aka some combination of m to the power of A times h bar to the power of B times alpha to the power of C times epsilon to the power of D. So if we write this out fully, this is kilograms to the power of A times kilograms times meters squared over seconds to the power of B times kilograms times meters to the fourth over seconds squared to the power of C times meters to the power of D. And if we write this out fully, and excuse me, let me increase my canvas size really quickly to 10,000. Okay. So if we want to write this out fully, then this is going to give us kilograms times A plus B plus C multiplied by meters, which is going to be 2B plus 4C plus D. And then we have seconds to the power of negative B minus 2C, like this. Now, this has to somehow match the units of energy, which is going to be kilograms times meter squared times second to the negative second. So if we write this out as a system of equations, we get A plus B plus C is equal to 1. We have 2B plus 4C plus D is equal to 2, and then negative B minus 2C is equal to negative 2. Okay, so now I want to solve this system, and I'm going to do that. I'm going to start by looking at this bottom term. I'm going to say, okay, I can set B plus 2C is actually equal to positive 2, which means that 2C is actually equal to 2 minus B, or C is equal to 1 minus half B. I'm going to plug this into the top, and I'm going to get A plus B plus 1 minus half B is equal to 1, or A plus half B is equal to 0, or if I wanted to move this to the opposite way around, then I could say B is equal to negative 2A. If B is equal to negative 2A, then I want to solve everything in terms of A, because remember, we have a set of 3 equations and we have 4 variables, so we're going to have one free variable. I'm just going to set mine to be A, in which case if B is equal to negative 2A, if I plug that back into here, then I get C is equal to 1 minus 1/2 times negative 2A, which is going to be, C is now equal to 1. Let's see, this becomes a plus 1 plus A. And then if we plug both of these back into our second equation right here, then we get 2 times negative 2A plus 4 times 1 plus A plus D is equal to 2. So in that case, negative 4A plus 4 plus 4A plus D is equal to 2. The A's cancel. We get 4 plus D is equal to 2, or D is just equal to negative 2. So at this point, we have solved the system of 3 equations, but it has 4 variables. So one of the 4 variables is going to be free. I have chosen A to be that free variable. So A can equal anything it wants in this case. For the simplest system, obviously I'm going to choose A to equal 0. So in the case where A is equal to 0, this combination of values is going to turn into A is equal to 0, B is equal to negative 2 times A, which is also going to equal 0. C is equal to 1 plus 0, which is just 1, and then D is equal to negative 2. So in that case, we have, let's see. Yeah, so our new system is going to be, let's move this over to this side. M to the power of A, H bar to the power of B, alpha to the power of C, and epsilon to the power of D. This is going to equal A is 0, B is 0, so these two both just go away. And then we have alpha to the power of 1 times epsilon to the power of negative 2, which is equal to alpha over epsilon squared. So we now have the first part of our desired energy expression. We have the alpha over epsilon squared. The next thing we have to do is we have to incorporate negative f of beta. So immediately, first off, let's go back up and find out what beta is. Beta is 2m alpha over h bar squared. Let's write that down. Beta is equal to 2m alpha over h bar squared. And what we mean by having this additional function of beta attached is that while the alpha over epsilon squared term has to appear because it has the units of energy, we also have to recognize that we can have additional terms as long as they ultimately combine to become dimensionless. So, I can have extra terms in this function, which let's not even call it a function of beta right now. Let's just call it an arbitrary function attached to alpha over epsilon squared. This can appear so long as this function has dimensionless units. So to do that, we just have to rewrite our system, this whole thing right here, but instead of setting it equal to 1, 2, and negative 2, we set it equal to just 0, 0, and 0 all around. So by doing this, we're basically saying, okay, is there a possible combination of these variables that we can attach that has no dimensions? And if it does, then there's nothing that stops us from attaching it on, because anything we attach of that form is not going to have any units, and it's just going to apply a numerical factor to our energy. So now let's solve this, and we're going to do the exact same thing as before. So let's see, from this point, I'm actually not going to use A as my free variable because it seems like there's an easier way to solve this here. I'm going to say B plus 2C is equal to 0, therefore B is equal to negative 2C. In that case, if I plug this into the top equation, then I get A minus 2C plus C is equal to 0, which means that A minus C is equal to 0, or A is equal to C. And then if I plug that into the middle expression, then I get 2 times B, which is negative 2C, plus 4C plus D is equal to 0, or negative 4C plus 4C plus D is equal to 0, or just D is equal to 0. Okay, so at this point, now that we have these 3 equations, let's write them out fully. So we have A is equal to C, B is equal to negative 2C, D is equal to 0, and C is just equal to any free variable. So obviously, like before, sort of the simplest system we can have is that C is just equal to 0. Because if C is equal to 0, then all these terms equal to 0. Then we have just, M to the power of 0, H bar to the power of 0, alpha to the power of 0, epsilon to the power of 0, which is just 1. This is valid because 1 has no dimensional units, so we can attach a 1 to our function without any problems, but this doesn't really help us. This is kind of a trivial solution. So in order to have a non-trivial solution, instead of having c equal to 0, I'm going to have it equal to the next simplest thing, which is I'm going to have c equal to 1 instead. Because remember, c can equal anything. So if c is equal to 1, then a is equal to 1, b is equal to -2, d is still 0, in which case our new units are going to be m to the power of a, which is 1, times h bar to the power of b, which is going to be -2, multiplied by alpha to the power of c, which is just 1, and then finally epsilon to the power of d, which is 0. So this is just equal to m alpha over h bar squared. So what this implies is that we can therefore attach any function in terms of m alpha over h bar squared to our earlier term of alpha over epsilon squared without causing any dimensional issues. So our general form for energy is going to be equal to alpha over epsilon squared times some function in terms of m alpha over h bar squared. So what we mean by some function of m alpha over h bar squared is that I can say, given constants, dimensionless constants, I can say, c times m alpha over h bar squared plus, c2 times m alpha over h bar squared plus dot 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 dot. And like if I want to include some other complicated stuff like sines and cosines and stuff, that's fine as well. Just ultimately, this is a numerical. The important thing is that this is going to come out as just a number with no dimensions. So because of that, there's nothing that prevents us from attaching it on to alpha over epsilon squared. Now, the thing that we have to remember is that beta is equal to 2m alpha over h bar squared. So we're missing some stuff. This is not 2m alpha over h bar squared. This is m alpha over h bar squared. But that being said, remember that this 2 here is just quite literally a constant. And constants don't have dimensions. So there is nothing stopping me from rewriting it as alpha over epsilon squared in terms of another function, which I'll call g of 2m alpha over h bar squared instead. There's nothing stopping me from doing this because, once again, this is a dimensionless function. I can attach as many other dimensionless variables onto it as I want, in this case 2, without any issues. It just changes the form of the function. Same thing. So the answer wants us to get negative alpha over epsilon squared times function of beta. There's nothing stopping me from just adding another negative onto here. I can rewrite this as negative alpha over epsilon squared times a new function, small f, of 2m alpha over h bar squared. By adding this negative, all that changes is that the form of my function changes a little bit. But it is still a valid way of writing out the form for energy. And with that, we are done with the second part. So now let's move on to the first part, which is plotting this actual function. Okay, so the final part is to sort of graph the resulting ground state function. And I'm going to say right now that I don't believe this is something that can be achieved within a reasonable span of time using just Python. Once again, sort of running into the limitations of using SymPy is that it doesn't work particularly well with these higher end equations like Bessel functions and stuff. So what I'm going to do is I'm going to show the result of me trying to plug this equation in. And what you see here is something called these j and y terms. They're also Bessel functions, but they are unmodified standard Bessel functions as opposed to the modified Bessel functions. Actually getting into detail for this would get way too complicated, but pretty much if we try to solve this exactly, we will not have a good time. So instead, sort of the closest thing we can do is pretty much just to guess and check, because from part C, we know the general form of a valid solution, which is square root of x times Bessel k times ig times x of xk, where ig is the order. So I plug in 4 for the order. And as sort of part D says in its hint, we have to sort of figure out the correct term for k. And there really isn't a good way to do this other than just plug in values of k and guess. So the way I did it was, okay, I start with k equals 1. And if I graph this, it's not really 0 at 0 point. Like, this is 1, So, you know, if I look at it, it's like, you know, is this equal to 0? At x equals to 1, and it's not exactly, so I can play around. So like, what if I do x equals 2? Okay, if I do x equals 2, I get this weird thing that doesn't seem to help me at all. So instead, let's go the opposite direction and go like x equals 0.5. If I do x equals 0.5, I get something that actually does seem to help. So it seems like there is an upper limit for x. So is it 1? Let's see. If I go x equals 1.1, or sorry, k equals 1.1, then that's still valid. What if k is equal to 1.2? That's still valid. Okay, let's do k equals 1.3. That is still valid. What if I do k equals 1.4? Okay, so evidently at some point between 1.3 and 1.4, the graph or the Bessel starts to break down. I don't know why this is a thing. I don't want to get into why this is a thing. Bessels are too complicated for the purpose of this basically upper division undergrad quantum mechanics, so I don't want to get into details about it. It's too mathematical. But at some point between 1.3 and 1.4, the equation starts to break down. So I'm just going to plug in, I'm going to basically test values between 0 and 1.3 and see which one sort of sticks the closest to the function going to 0 at x equals 1. So, you know, let's do like 0.7. And it seems like it just went over a little bit, so let's go down to like 0.6. Okay, so if I go down to 0.6, it seems to go forward more. So let's do instead like 0.4. That's almost there. Let's do like 0.3. Okay, that seems to be like between 0.4 and 0.3 at some point, the zero crossing sort of goes from one side of 0.5 to the other side of 0.5. So let's do like 0.35. Okay, that's about as close as I'm willing to get at this point. If you wanted to be more accurate, you can do like a sweep using something like a for loop and like isolate out different terms, but I don't really think that's a good use of my time. So I'm just going to do this very rough guess and check method and see that at k equals 0.35, this graph matches the boundary conditions close enough that I'm willing to say that the actual ground state wave function looks something like this. So what I would then do is I would just get rid of everything below x equals 1, because all of this doesn't matter, because remember, we have our well shifted over to epsilon equals 1 anyway, so the wave function just has to go to 0 past x equals to 1. So I ignore everything to the left, and I just write out the graph looks something like this to the right. And with that, we've pretty much done as much as we can for solving this. At least in my opinion, we've done. But, you know, I'm not a computer scientist, and I do not, you know, I use Python as a means to an end, not as a way to, like, my passion is not coding, it is physics. So there could very well be other methods for doing this that are much more optimized and better than mine, but this is just how I have chosen to do this problem.